Assalamualaikum warahmatullahi wabarakatuh, and welcome back to my video. So today we will continue with example 2 of magnetic circuits. So what the question says. So figure 1.2 shows a ferromagnetic core whose mean path length is 40 centimeters. So I will show later how the figure looks like. So there is a small gap of 0.05 centimeter in the structure of the otherwise whole core. Okay, so the cross-sectional area of the core is 12 centimeters square. So this is the A, okay, the area, and the relative permeability mu r core is 4000. So, and the coil of wire on the core is 40 or 400 turns. So this is actually the N or number of turns. So assume that fringing in the air gaps increases the effective cross-sectional area of the air gap by 5%. So given this information, find a total reluctance, okay, of the flux path iron plus a gap. So we have R, E, Q, okay, the total reluctance, and B, the current period to the current required to produce a flux density B of 0.5 Tesla in the gap. So back to the fringing effect. So this is nothing but actually the effect that occur in between two core, especially in the area of air gap here. All right, so let me draw you the 2D diagram. Okay, we have the upper core, so we have the lower or the bottom core. So we do have magnetic lines, right, or magnetic field. So lines is a lines of flux again, and due to the air gap, so we have the fringing effects. Okay, here this is the fringing effect. Okay, or the fringing flux, the flux that's coming out of the core parts. All right, so this is the fringing. Fringing, fringing flux. Okay, so it is somehow cause the area, okay, the cross-section area within the air gap is 5 or certain percent bigger. In this particular example, it is given by 5%. All right, compared to the one in the core. Okay, this is the core. All right, 5% bigger or 5% wider from the core. Okay, we will see in detail how the calculation works. Okay. So solution. So this is a figure 1.2. So we have a rectangular core over here. The given information from the question. So we have LC, the mean path length of the core, which is 40 centimeter here. Right, LC equal to 40 centimeter. It starts from here, for example. Okay, this part or this root down here. Okay, here and here. So the whole or the entire core, the mean path length is 40 centimeter. Okay, so this is again where the flux is flowing, okay, inside the core. So what else? We have AC. This is the cross-sectional area of the core, 12 centimeters square. All right, this one. Okay, so let me color in the different. Okay, we use a different color. So let's say this is the yellow color. Right, this represent the AC or the cross-sectional area of the core, which is given by 12 centimeter square. Okay, and then the third one, the third information given is mu r, the relative permeability of the core. Okay, and is number of turn, which is 400 turn here. Okay, the number of turn of the coil is 400 turns. So this is what I explained earlier. The A or the cross-sectional area of the air gap is somehow 1.05 multiplied by AC. Okay, because the fringing effect over here here, okay, the fringing flux over here give 5% bigger or wider than the A of the C here. Okay, so the effect, this is 5% bigger than the EC. So we can say that the cross-sectional area of the A gap is actually 1.05 times the AC. Okay, and then what about the flux density B? So this is 0.5 Tesla. Okay, so first of all, so make sure you draw the magnetic circuit. Okay, so try to draw the magnetic circuit according to the structure given. So we have first the magnetomotive force F equal to Ni, and then we have the flux and its direction as well, and the reactance of core plus reactance of air gap. So we do have this symbol which is representing RC as well as RA. So you have to start or kick off with magnetic circuit always. Okay, and then A, find Req, the total R reluctance, and then B, find the IAG, or the current that induced B equal to 0.5 Tesla in air gap. So and then using this formula, RC or R equal to L over mu A. Okay, so expand the equation, we have LC, okay, mu R, okay, mu naught AC. Okay, so we have 0.4. This is from a question. Remember, you need to convert into meter. This is actually from 40 centimeter, the mean path length of LC. Okay, over mu R, the relative permeability of the core, this is provided in question, 4,000. So this is a fixed constant. We have mu naught, which is 4, 5 multiplied by 10 to the power of negative 7. So this is fixed for mu naught, okay, all the time. And then the AC, again, this is the cross-sectional area of C here, right? 12 centimeter square, but make sure you convert into SI unit, M square. So you have to divide by, for example, here, okay, we have 1, 2, 3, 4. So we have another 2 in order to convert into meter square. All right, here. So 0.0012 meter square. And giving LC or RC, the core reluctance, 66,300 ampere turns per Weber. Oops. So per Weber. So make sure you write the full and the correct unit. Okay. So ampere turns per Weber. And on the other hand, so we have the air gap reluctance, okay, or the reluctance of air gap RA, again equal to LA over mu A. And expand the equation, we have this is not A, this is not C, sorry, this is actually A, so equal to or divided by mu R mu naught A. So again, this is actually from question given by 5 centimeter. Okay, so convert to sorry, this is not 5, but this is how much? This is actually 0.05. Sorry, okay, this is actually 0.05. Okay, the length of or the mean path length of the air gap. So 0.05 centimeter here is, okay, let me correct, 0.05 centimeter. So once you convert into centimeter, again you need to divide by 100. Okay, so dividing by 100 giving 0.0005 meter. Okay, over mu R, mu naught A. So what is mu R? Mu R is simply 1 here. All right. Okay, due to air gap. So the relative permeability for air gap is 1. Okay, mu of air gap is actually 1. Okay, this is mu naught. Again, same value like this one, 4, 5 times 10 to the power minus 7. So this is the critical part. So you have to be extra careful because it consists of fringing effect, which is 5% bigger than the core area or the core cross sectional area. Okay, so multiply by 1.05, okay, 12 centimeter square. So you need to again convert into meter square, giving 0.00126 meter square. And solving this, giving us the reluctance of a gap is actually 316,000 ampere turns per waver. Okay, therefore R equal or the total R. So we have RC plus RA, 380,000 ampere turns per waver. Okay, and then when flux density equal to 0.5 Tesla at the air gap, so what is the required current to be injected? I. Okay, so knowing that F equal to flux of phi R, and then we have phi over here equal to BA, and F equal to NI. So substitute this and this into here, and sorry, not here, but this is into here, phi, and here F to here. Okay, so I cancel this one. So giving NI equal to BAR, rearrange in terms of I. So we have BAR over N. So substitute of the value provided or the value we just calculated into this particular example. Oh, sorry, in this particular equation. So again, be extra careful with the value you take for A because this is referring to AC, right? Oh, sorry, AG or A gap, not AC. So this is the cross-sectional area for A gap because the question asks you to calculate the required current produce flux density in the air gap. All right, so be extra careful. So the A gap is actually 0.00126 meters square, the one you counted in the factor of fringing effect. Okay, so 0.5 Tesla for B. So this is for 382,000 for the total R or reluctance. This is actually from here, coming from here. Okay, and over N number of turns, and yielding I equal to 0.602 ampere. Okay. So jumping over to example 3. So the question describes that a simplified rotor and stator for a DC motor is shown in the figure 1.3. So we look at into the figure more details later on. So the mean path length of the stator is 50 centimeter. So the question has already calculated the length for you, and its cross-sectional area also has been provided here, which is 12 centimeters square. So the mean path length of the rotor, so since we have two division or two part, which is a stator here and rotor, so the next mean path length is particularly for for rotor, which is 5 centimeter, and its cross-sectional area also may be assumed to be 12 centimeters square. So this is identical to the stator cross-sectional area. So each air gap between the rotor and stator is 0.05 centimeters square. So since we have two sides of air gap, so the upper and the below air gap, and each of the length is equal 0.05 centimeter wide, and the cross-sectional area of each air gap, including the fringing factor, is 14 centimeters square. So the iron of the core has a relative permeability. Again, this is mu r 2000, and there are n number of turns, 200 turns of wire on the core. If the current in the wire is adjusted to be 1 ampere, this is the value of I. So what will be the resulting flux density? The resulting flux density B in the air gaps B. So we are going to calculate the flux density in the air gaps. Okay. This is how the figure or the cross section looks like. So we have the stator part, which is the steel component, all right, of the DC motor, for example. In this particular example, so we have here is the spinning part, okay, namely rotor. All right. So these are all the information provided in the question. So as the mean flux length of the stator, which is 50 centimeter here all the way, all right, here to here and here to here, is given by 50 centimeter. So we have E as the cross-sectional area of the stator, 12 centimeter. So if you can see here, okay, again I change the color to make it more better. So the green one is here is the cross-sectional area of the core, okay, and given by 12 centimeter squared. So what about the rotor mean flux length? 5 centimeter is over here. All right, so the motor length over here, okay, or you can simply say this is the diameter of the rotor. So the same or the identical value of the cross-sectional area of the rotor, 12 centimeter here, and inside this one also same. Okay, so we have the air gap length or distance, which is 0.05 centimeter. Okay, so in between, okay, change the color again here. All right. Now, so this is the first air gap, the upper one, and the second one between rotor and stator. Okay, so we have air gap 1, and then we have the second air gap. So particularly for the top and the bottom. Okay, in between stator and rotor, and again rotor and stator. So again, the mean flux length is given by 0.05 centimeter, and the the cross-sectional area, okay, of the air gap, including the fringing factor, is somewhat bigger than the area of the stator of the rotor itself, okay, which is 14 centimeter square here. Right? Try to compare with this one, and try to compare with this one. So mu out, the mu probability of the core is 2000. Number of turn here, okay, number of turn, n equal to 200. And what is the flux density when I equal to 1 ampere? So remember, start with magnetic circuit, okay, CCT for example. And we have again the magnetomotive force over here, F equal to Ni. This is the terminal positive and negative. So we should have here the direction of flux, where the flux goes. And we have the first reluctance, which is stator reluctance. And then we comes to the first air gap reluctance, Ra1. Then we move on to the rotor reluctance, and again another air gap 2 reluctance. All right, so the stator reluctance have been concluded into one stator, one representative here. Okay, and so let's start with the first calculation, where we have stator reluctance Rs equal to Ls over mu R mu naught. Okay, so this is the value provided or given in the question, 2000. So remember, so this one, don't forget, this is for 5 multiplied by 10 to the power of negative 7. Okay, so we have the ES, the cross-sectional area for the stator, which is 12 centimeter squared, convert into meter. Okay, don't forget. And then again, the mean flux length of the stator, which is 50 centimeter or 0.5 meter. Okay, so don't do mistake over here. Okay, solving this, giving Rs equal to 166,000 ampere turns per Weber. So next, the Rr, the rotor reluctance, we have Lr over here. So let me change again the color. So we have Lr over here, the mean spark length of the rotor. So we have mu r, the relative permeability, the mu naught, as well as the Ar. Okay, 0.05. Okay, for the rotor mean spark length, just now we have 5 centimeter, or we can simply say this is the diameter of the rotor. Okay, 5 centimeter convert into meter, don't forget, divided by 2000, the relative permeability. So the mu naught over here, okay, and then the AR, the rotor cross-sectional area. So giving 16,600 ampere turns per Weber. And here we have the air gap reluctance LA over mu r mu naught A, EA, so 0.000 meter. So this is converted from how much just now? So we have actually 0.05 centimeter. All right. So 0.05 centimeter. Okay, you convert to meter. All right. So divided by 1 again. This is the mu r, the relative permeability for A gap. All right, for A gap. So mu naught for pi times 10 to the power of minus 7, and the AA is 14 centimeter squared. And again, the resulting value of RA is 284,000 tons per Weber. So the equal R, or the total R, we have RS plus RA1. Okay, so plus R plus RA2. Since we have two air gaps, so make sure you include both air gaps reluctance. Okay, 166,000 plus 284 plus 166,000 plus 284,000 ampere turns per Weber. So the total R is 715,000 ampere turns per Weber. So what about the MMF? The magnetic force F equal to Ni. Okay, substitute the value of N 200 and ampere, or current 1 ampere. So this is giving us 200 ampere turn Weber. So the total flux K phi equal to F over R. So for 200 ampere turns over here, okay, over R, this is actually Req, or the total R. Okay, so altogether we have flux equal to 0.00266 Weber. So what's next? Finally, the flux density in air gap B equal to flux over A, or phi over A. So take the value we just calculated here into here B, and don't forget this is which A? The A gap A. Okay, A, G. Okay, back to the question. So be extra careful. So we have the flux density injected by 1 ampere current over here occurs at the A gap, okay, is equal to 0.19 Tesla. All right, now moving on to the second principle, transformer action. So some of the definition on how to understand this particular principle. So a changing magnetic field causes a voltage in any circuit through which it passes. The change can be caused, so the changing magnetic field, we try to look into more detail. What does it mean? So it is actually caused by the changing the current, okay, caused by changing the current, producing the magnetic field, or by moving the sources of the magnetic field. So this is the best illustration or best diagram we can understand. So since we have the magnetic bar over here, so we can have two options, whether we can move, all right, so move the source of the magnetic field, which is we try to move this one. You can see the motion or the direction of the motion, okay, all right. So we may also increase the current, okay, and here the magnetic field decrease and thus voltage is induced. Okay. Similarly, we have this rectangular type of core. All right, we have a coil over here, another coil on the opposite side, and the transformer. This is okay. Called a transformer, magnetic field increasing. Okay, the turn ratio is 2:1, twice as much current needed on right here. So balance current on left, therefore half voltage. So this is why we call it this phenomenon as the uh, stepping down transformer or step down transformer. So basically this is how we induce the voltage. And again, according to Faraday's law, so what the Faraday's law says is if a flux passes through a turn of a coil of wire, so voltage will be induced in the turn of wire that is directly proportional to the rate of change in the flux with respect to time. Or in mathematical form, so E induced, the voltage induced in the N turns of coil is equal to negative N d phi over the dt. So this is the changing, the rate of change in the flux, okay, with respect to of time. So negative is meaning the opposed induced magnetic flux. Okay, so yes, a voltage induced in the N turns of coil. All right. This is the figure. We can have a better understanding. So since we have our coil over here, okay, this is the connector. So we have a number of turn. Sorry, this is the core. Okay, we have a core, and this is the connector, the wire. So we have number of turn N. So this is where the flux goes. Okay, so what happened according to Lenz's law? So the direction of the voltage built up in the coil is such that if the coil ends were short circuit, so these both ends were short circuit, it will produce current that would cause a flux opposing the original flux change. So this is the original here. All right, so the increasing flux, and then what happens if we short or we connect both end of coil, so we producing the opposite current direction, and thus induce the opposed flux, okay, direction of opposing flux. So this is where this negative sign is coming from. So again, the magnitude of the voltage in the ith turn. So let's say we have ith turn of the coil. So E induced again equal to the rates, the changing rate of the flux over time. So we have d by I over dt. If there are n turns, the total voltage on the coil, so we have induced voltage is a summation of E I equal to 1 up to n. So the number of turn over here. Okay. So E, so take from here, okay, we see the changes rate of flux over time. Okay. And then we try to simplify the equation, and from here we know that this is actually the flux linkage. Okay, so the lambda here is d lambda over dt is the flux linkage. So unit of induced here, the flux linkage unit, sorry, here, or the lambda is actually Weber turns. Okay. Then this flux linkage is actually the flux in core across which voltage is induced. Okay, so we can simply say that this is the flux that's linked up from one coil to another, one turn to another, in order to produce or to induce voltage. All right. Okay, thank you very much for watching. So we will continue in following video. Take care and have a nice day.